Unveiling the mystery of little red dots, not faster than Eddington. Imagine a universe filled with enigmatic celestial objects known as little red dots, or LRDs for short. These mysterious entities have been spotted in deep space images captured by the James Webb Space Telescope, JWST, leaving astronomers intrigued and puzzled. However, a recent study has shed light on their nature, revealing that they are not super-Eddington objects, despite their peculiar characteristics. LRDs are believed to be young, supermassive black holes nestled at the cores of ancient galaxies. Observations indicate that they share many traits with active galactic nuclei, AGNs, such as quasars and blazars. One notable feature is the broad emission lines in their spectral signatures, which suggest rapid movement of material around a dense central mass. Additionally, they emit minimal X-ray and radio radiation, hinting at the presence of a thick, ionized gas cloud enveloping the source. This scenario aligns with what we would anticipate from a rapidly growing black hole in a nascent galaxy. However, there's a potential hiccup in this hypothesis. AGNs derive their luminosity from the superheated accretion disks surrounding their black holes, which produce copious amounts of X-rays. To shield these X-rays, the surrounding gas cloud would need to be incredibly dense, potentially spanning galactic dimensions. Such a cloud would also obstruct much of the visible and infrared light we observe from LRDs, necessitating an extraordinarily high energy output to match their brightness. This raises questions about whether LRDs exceed the Eddington limit, a theoretical cap on the rate at which a black hole can consume matter without being repelled by the intense radiation it generates. Black holes grow by pulling in gas and dust, which heats up and emits light as it compresses. However, this process creates a feedback mechanism that limits the black hole's growth rate, known as the Eddington limit. A black hole can theoretically surpass this limit temporarily, akin to eating rapidly and then expelling excess energy through a powerful burst. This could account for the absence of intense X-rays from LRDs, as the black hole might be consuming material too quickly for X-ray buildup. Yet, a recent study challenges this notion. Detecting X-rays from AGNs is challenging, and researchers often capture only a few photons from each LRD. To overcome this limitation, scientists combined observations from 55 different LRDs in the Chandra Deep Field South into a single simulated entity. This approach allowed them to analyze the statistical optical depth of the surrounding material and the overall intensity of typical LRDs. Their findings revealed that while the ionized gas clouds around LRDs are substantial, their total energy output does not exceed the Eddington limit. One plausible explanation for these results is that the supermassive black holes at the centers of LRDs may not be as massive as initially thought. Consequently, they could emit sufficient light at non-obscured wavelengths without generating the high-energy X-rays characteristic of more contemporary AGNs. Although there is still much to uncover about LRDs, this research demystifies some of their previously perplexing attributes. In conclusion, while LRDs continue to captivate astronomers with their unique properties, recent studies provide valuable insights into their nature. The debate over whether these cosmic phenomena can break the Eddington limit remains open, inviting further exploration and discussion.